Continuing from Introduction to 3.1, we're going to now look at some notation for derivatives. The first one that you've already seen is the f with the little tick mark, which we call f prime of x. And this is notation for the derivative of f at x. That is what this symbol means. It's also read, like when you read it, as f prime of x. It has the same meaning. You might also see this written as y with a little tick mark, which is basically y prime. Or you could think of that as the derivative of y. And for you Transformers friends out there, or fans out there, sometimes I like to write Optimus Prime, just to remind myself what the little tick mark means. All right, then for the second notation, you'll see this one a lot too. The dy dx, which basically stems from the idea of slope. So if you remember, slope of the tangent line was change in y over the change in x. This is like how you find the slope of a line. And the dy and the dx is when you take the limit of this slope as the change in x goes to 0. So that's where this came from, kind of the same idea of change in y over the change in x as the change in x approaches 0. And we read this as the derivative of y with respect to x. That's how we say it, with respect to x. That's what that means. Derivative of y with respect to x, dy dx. And just so you know, it means the same thing as y prime. Just another way of writing the same thing. And then similarly, you've got df dx, which means basically the same thing, just changing y with f. Derivative of f with respect to x. Wait, I didn't write respect. With respect to x. So this is really the same thing as f prime of x. And then the last one, which is used primarily when giving like formulas for derivatives, is d dx of f of x. d dx of f of x means the same thing as derivative of f with respect to x. So whenever you see this, f prime of x, or this, y prime, or dy dx, or df dx, or d dx of f of x, they're all referring to the derivative of f at x. Moving on to our first graphing example. What it's asking you to do is to use the graph of a function. So let's just go ahead and call this function f of x. That's what's given to you. And you're being asked to sketch a graph of the derivative of that function. So they want you to graph f prime of x using only the graph of f. What we need to remember is what f prime of x means. It means the slope of the line tangent to f at x. That's what f prime of x means. So what we need to do is we need to look for obvious slopes. And the most obvious are the zero slopes. So what we're going to do is take a look at this graph. And we're going to locate where the slope of the tangent line is equal to 0, because that's the most obvious. Because the zero slope is basically a horizontal tangent line. And we've been talking a lot about that lately in classes. When you have a horizontal line, its slope is 0. So that would happen right at that point and at that point. Another thing that you need to remember is the x values of the derivative are the same as the x values of the function. So I basically have found that f prime of -2 is 0. because the slope of the line tangent to the curve when x is negative 2 is 0 because it's horizontal. And I've also found that f prime of 1 is 0. So those are 2 points on the derivative. This is the point negative 2 comma 0, and this is the point 1 comma 0. These are points actually on the graph of the derivative. Notice I kept the same x-coordinate that was on the graph of f, but I replaced the y-coordinate with the slope of the line tangent to the curve at that point where x is negative 2. So let's make a little chart here, because I noticed that this graph goes all the way from negative infinity to positive infinity. So let's have it go from negative infinity to that first 0 slope, negative 2, and then from negative 2 to the second 0 slope, which was at 1, and then from 1 to infinity. And these, by the way, are just intervals of x values. So these guys, they're intervals of x values. So I notice that from negative infinity to negative 2, so basically from here and to the left, the function f is increasing. The function f is going up from negative infinity to negative 2. So what that means is that the slopes, that's this guy right here, the derivative is the slopes of all the tangent lines, those would have to all be positive slopes. Because if you take a look, let's say I were to pick like this x value right here. Well, yeah, or actually let's use this x value right here. Go down to the curve and draw a line tangent to the curve at that point. It would have a positive slope. In fact, it would have a really steep positive slope, because that's tangent to the curve there. And then if I were to pick any other point between negative infinity and negative 2, I would have maybe this one here. That's another positive tangent line slope. Maybe this one there. Notice all these different slopes, the lines are going up every time because the function's going up. They're all positive. Then between negative 2 and negative 1, the function is going down. Between those 2 points, the function is decreasing. So if I were to pick some x value between negative 2 and 1, like 0, for example, if I picked this point right here and drew a line tangent to the graph right there, it would look something like this, and it would have a negative slope since it's going down. So all of those slopes between the x values of negative 2 and 1 are all going to be negative slopes. And then I noticed that between 1 and infinity, or just from 1 on, the function's increasing again. It's going up again. So I noticed that my slopes are all positive for any x value that's greater than 1. So I'm going to use this information and this information to sketch the graph of f prime. I don't have a lot of room left, so I think I'll do that down here. So remember, I had these 2 points because I could tell exactly that those tangent line slopes were 0 because they were horizontal. And that was when x was negative 2 and when x was 1. Because remember, you keep the same x values as the original function. Only the y values now for your derivative are the slopes of the lines tangent to the curve at that x value. So these y values are both 0. And then I know that my slopes are all going to be positive to the left of negative 2. So my graph is going to be up here. But not only are they positive, but notice that as the x values move toward negative 2, the slopes are getting less and less steep. In fact, they're getting to the point where eventually they're going to hit 0. So it's kind of like I have these really high positives, and then they get less and less steep as x moves towards negative 2. Then between negative 2 and negative 1, all my slopes are negative. So they're all down here. Excuse me, down here. And notice that they start off pretty gradual. Like this one kind of starts off not that steep. maybe a slope of negative 1/2. And then it gets increasingly more and more steep. And then as it gets close to 1, the slopes get less and less steep again. So it's kind of like the values get really negative, and then they start getting closer to 0 again as the x values move toward 1. Then on the right of 1, you have slopes that are getting steeper and steeper and steeper again. So it's kind of like that. And so that would be a rough guess of the graph of f prime of x. So just to recap, we first found the 0 slopes. The 0 slopes happened when x was -2 and when x was 1. And then we found those points on the graph of f prime of x. Then we sort of made a little sign chart from -infinity to infinity. These are all little intervals of x values, and I broke it up based on where the 0 slopes were. So I went from -infinity to the first 0 slope, and then between -2 and 1, between the two 0 slopes, and then to the right of the last 0 slope. Whenever the function was going up, the slopes were positive. Whenever the function was going down, the slopes were negative. So then these are positive slopes, these are negative slopes, and these are positive slopes. And there's the graph of f prime. This example has the opposite thought process as the last example, in that what they've given us here is the graph of f prime of x. They've also given us a point on the graph of f of x. And they've told us that f is continuous, which is code for connected. So let's examine what we have here. We basically have what looks like a piecewise function with a jump when x is 1. And these are constant. So I can see here that the values of f prime of x are 2 for this top step, and then down here the values of f prime of x are -1. And I'm just going to have it stop right here, so we'll have it stop when x is 4. So it looks like when x is 4, or sorry, between 1 and 4, it looks like the slopes are 2. So that's referring to the slopes of the tangent lines. And that's true for all tangent lines between the values of 1 and 4 for x. Then down here, maybe we'll have it stop right here at -4. So it looks like when x is between -4 and 1, that the slopes are all equal to -1. And what else I want you to notice is that the slopes are constant. This is a constant rate of change. So that means that f of x has a constant rate of change on those values. So that could only mean one thing. In fact, let's continue this thought. That could only mean that f is linear. Because linear functions are the only ones that have constant rates of change. Any other function would have curves. So this function has no curves. Okay, so let's go ahead and make an attempt at its graph. Now remember, f of x and f prime of x, they maintain the same x values. I'm not going to change x values, so x values stay the same. And so x is going to be between -4 and 4. And I'll start with the given point. So 0, 0 will be my starting point. Now 0, 0 is part of this set, because when x is 0, if you look at the graph of the derivative, the slope is -1. In fact, the slope remains -1 between the x values of 0 and 1. So between these x values, the slope is negative, meaning it's going to drop down 1 and over 1. And it stays that way. It has that same slope of going down 1 over 1, down 1 over 1, all the way to negative 4. And so that's the graph of f of x to the left of 1. Some of my points were off there, so let's fix those. Okay, and then to the right of 1, I'm going to follow this slope. So the derivative was 2, and that's true all the way from 1 to 4. So that means the slope of the tangent line is going to go up 2 over 1. Up 2 over 1. And there's my graph of f. Oh wait, sorry, let's not have an arrow there because we were going to have it stop at 4 and negative 4. Okay. So notice that on the right side of this function, the slope is 2. On the left side of this function, the slope is negative 1. So if I were to draw a tangent line, and by the way, a tangent line, a line that's tangent to another line is basically just lying on top of it pretty much. It's the same line. So the slope here is 2, and then the slope here is negative 1. Notice that we had to have f connect. The reason why I made it connect there is because it's continuous. F is continuous, so it's connected. But I would like you to take a note of the fact that the derivative was undefined at 1. That's kind of just a segue into our next chapter, because there was a sharp corner on the graph of f, and the slope on the right was not equal to the slope on the left, and therefore the derivative had a big jump in it. So just something to keep in mind for future. Last example is we're given this equation of a curve, y equals x to the third. We're asked to find the line that is tangent to the curve at the point 1, 1. So in order to write the equation of a line, we need to have a point and a slope. And the equation that I always like to begin with is just this generic point-slope form. And to use this form, I need a point, which in this is x1, y1, and a slope, which in this is m. So here are the coordinates of my point, and here is my slope. So I need to find those two things. Well, I'm in luck. They gave me the point. So I have the point. And that's 1, 1. I need to find the slope. So the slope is equal to f prime of 1. The slope of the tangent line is equal to the derivative of f at that point. So we're going to go ahead and use the formula for finding the derivative of a point at x equals 1. So that would be the limit as x approaches 1 of f of x minus f of 1 all over x minus 1. So right here, this comes from, I'll do a little memory bubble over here, the formula f prime of a equals f of x minus f of a all over x minus a. So I'll go ahead and plug in f of x, which is x to the third, minus f of 1. So if I plug 1 in there, I get 1 to the third is 1 all over x minus 1. When I substitute the 1, I get 0 over 0, so I need to do more work. So I'm going to factor the numerator into x minus 1 and then x squared plus x plus 1 all over x minus 1. Then I notice that the x minus 1's cancel out, and I have limit as x approaches 1 of x squared plus x plus 1. And now I can find that limit by simply substituting. I can plug the 1 in here. I get 1 squared plus 1, and that gives me 3. So that is my slope. So f prime of 1 equals 3, and that's my slope. So all I have to do now is just plug that 3 in for the m, and then the 1 and 1 in for x1 and y1, and I get y minus 1 equals 3 times x minus 1, and I am done. That's my answer. The last part asks us to find the line that is normal to the curve at the same point. All you need to know is that normal means perpendicular to the tangent line. And to find a perpendicular slope, you basically just flip the regular slope and change the sign. So the perpendicular slope would be -1/3. And the point is still the same. And using the same formula here, I just do y minus 1 equals -1/3 times x minus 1. And that would be the equation of your normal line. Thank you for watching. Oh, and also don't forget to complete numbers 6, 7, and 8 from the 3.1 worksheet that you were given today in class.